Okay, so in this lecture I am going to talk about the concept of Fourier integrals and Fourier transform. Okay, so let us recapitulate that the characteristic property of Lta system was if it is driven by sinusoidal function, like this sinusoidal function, the response also be sinusoidal in characteristics. Okay, so this particular property is valid only for sinusoidal input. In case you take the same Lta system, then if you apply some non-sinusoidal input, let's say like square wave like this, then the output cannot be like a square wave. Okay, so output cannot be a square wave, it will be completely different. So only for sinusoidal inputs the output will be sinusoidal, and we have seen that also. Let's say the input is x of t and the output is y of t. What is y of t? Y of t is equal to h of j omega times x of t, provided that x of t is sinusoidal function. So recall this property. No other periodic function will provide such characteristics, only sinusoidal functions. Even though here the input is periodic, it is not valid. So the matter is not periodic. The thing is, it should be periodic as well as sinusoidal. And once this particular property is satisfied, then we brought in additional concept like a frequency response, as I said, h of j omega. Then impedance concept, output divided by input or input by output. So okay, so which simplifies the analysis of linear system which are driven by sinusoidal excitation functions. Now this naturally led us to inquire how we can analyze the linear system when the Lta system is driven by periodic non-sinusoidal excitations. You take the Lta system, but now the input is not periodic. No, sorry, periodic but non-sinusoidal. In this case, what will be the output? Okay, so and the Fourier series came in very handy in this context. So whenever you have periodic non-sinusoidal functions like this, or we have seen the example like this, these are non-sinusoidal functions, periodic but non-sinusoidal, periodic non-sinusoidal. Whenever you have these kind of things, then you can represent in terms of Fourier series. Again, Fourier series represents in terms of Fourier series representation is in terms of sine waves, and in the sense that any non-sinusoidal periodic function can be thought of as composed of several sinusoids. If you recall the definition, then sigma n is equal to 1 to infinity a n cos n omega naught t plus sigma n is equal to 1 to infinity b n sin n omega naught t, right, plus a naught. Therefore the periodic non-sinusoidal function can be represented in terms of sinusoidal function. Again, if you have sinusoidal function, then you are done, your job is over. Okay, input is sinusoidal and periodic, and the output also again periodic and sinusoidal, so no problem, your job is very simple. Okay, so and by virtue of linearity, superposition principle, we can find the response to each one of the excitation functions. Now the input doesn't contain only one function, you have infinite number of functions, here also infinite number of waveforms, and superpose the response to get the total response under steady state conditions when the linear system is driven by periodic but non-sinusoidal excitation function. Naturally, we would like to see whether this analysis can be carried forward to a case where the excitation is non-periodic. The first case is, let me write down clearly. First we started with periodic and sinusoidal, no problem. The output is very simple, you can write. What is y of t? Y of t is equal to h of s times x of t. And the second case is periodic but non-sinusoidal. The example is like a square waves like this, or triangular wave like this, or whatever it is. So in this case, what you do, represent these guys in terms of Fourier series, and Fourier series has n number of components, okay, where n goes to infinity, like sin omega t, omega naught t, sin 2 omega naught t, and up to sin n omega naught t. There are many components. Similarly, cos omega naught t, it may cos 2 omega naught t, and so on up to cos of n omega naught t. There are many components. So you apply these components to the Lta system, because now the input is sinusoidal. So we moved from non-sinusoidal to sinusoidal. And now if the input is sinusoidal, then output also sinusoidal. That is the second part. Now naturally one can ask, like, now the third case is non-periodic. Non-periodic means what? Aperiodic. Aperiodic, and also it is non-sinusoidal. Not necessarily it will be sinusoidal. Okay. Then in this case, what we will do? We would like to see whether this analysis, these two methods, above said two methods, can be carried forward to the case where the excitation function is no longer periodic, it is aperiodic. So we will call such excitation functions aperiodic functions. If the input is aperiodic, then how we can analyze? So when a function is aperiodic, one can ask, is it possible for us to consider that a periodic function has composed of sinusoidal functions of different frequencies? Surprisingly, the answer is yes. Okay, and this constitutes the discussion of the subject matter of our discussion under the topic of the Fourier integral and the Fourier transform. Okay, we will derive this Fourier integral and Fourier transform. Okay, now as I said, this Fourier series method, whatever we developed, that we can try to use for aperiodic signal also, because when Fourier proposed that any periodic function can also be thought of as composed of several sinusoids, he did not gain immediate acceptance from all the mathematicians. Actually, the fact that periodic function can be composed of several trigonometric functions of different frequencies, and this fact is known even before Fourier, even though the earlier work did not carry out this analysis to be logical extent. But it is a singular and unique contribution of Fourier to extend this kind of Fourier analysis to aperiodic functions as well. So periodic function can be represented in terms of sinusoids. It is not very important result. Not very important result of Fourier. But what he proposed is even aperiodic signals also can be represented in terms of sinusoids. So this draws so much attention on the work. Very important result. So this is we are going to study under the topic of Fourier transform. So what he really said was that if you have a periodic function, it can be thought of as the sum of several sinusoidal with infinite number of frequencies. See, in the summation it goes up to infinite number of sinusoids if you have a periodic function. So infinite number of such a small components, each with a vanishingly small amplitude. As I said, A1 is greater than A2, A2 is greater than A3, and so on and so forth. If you take AN has very small amplitude. That means vanishingly small amplitude compared to A1. And if you put all of them together, you will get a given periodic function. Maybe this square function, or this half-wave rectified function, or a triangular function like that. Okay, so let us see how we go about splitting up a given periodic f of 2 into various let us see how we go about splitting up a given aperiodic signal into various sinusoidal components. So the input is, the given signal is given x of t, which is aperiodic. So from aperiodic we need to set up into various sinusoidal components. So our ultimate goal is we need to represent in terms of sinusoidal components. Why? Because sinusoidal is the only signal that gives the sinusoidal output. No other signal has that kind of property. And this aperiodic signal extends from minus infinity to plus infinity. And what happens beyond minus infinity and plus infinity, it doesn't matter for us. Okay, we will not bother about it. So any periodic function can be thought of as any aperiodic function. Aperiodic function, this is a very important statement, please try to understand. Any aperiodic function can be thought of as a periodic function, aperiodic space, okay, can be thought of as a periodic function with the period extending from minus infinity to plus infinity. Suppose for example I have the periodic function like this. Now let us say this is my period, minus t0 by 2 to plus t0 by 2. So total period is t0. Now what I am saying is, you make this t0 to go to infinity. That means the next pulse is going to occur after infinity. So you have only one pulse, and after that the next pulse comes after infinity. We don't know where it comes, and previously the pulse occurred before infinity. So from the range from minus infinity to infinity, I have only one pulse. So in this case, the next pulse is going to occur after infinite duration. So what is the period now? Period is equal to infinity plus infinity to infinity. Again let me call infinity. Therefore the aperiodic function can be thought of as a periodic function with a period extending from minus infinity to plus infinity. That means what? It occurs just once. When I say period is equal to infinity, that means it occurs just once. Afterwards it will not occur. So that means the period of this is going to be infinity. So now what is the consequence? The consequence is that the frequency of this is 0. Why? Frequency is equal to 1 over t0. Then 1 over t0 is infinity, therefore 0. What is the frequency? 0. That means what? It never occurs. It occurs only once. Okay, it will not repeat itself. And if the frequency of this is 0, then how are we going to think of various harmonic components, right? Because in Fourier series we said we had omega naught, 2 omega naught, 3 omega naught, and so on and so forth. But here what we are saying, f naught equal to 0, that implies omega naught is equal to 0. If omega naught equal to 0, then you have 2 omega naught is equal to 0, 3 omega naught is equal to 0, and so on and so forth. In this case, how will you think of various harmonic components? Because in the Fourier series, various frequency components are integral multiples like 2 omega naught, 3 omega naught of the fundamental frequency. So how are the here the fundamental frequency is 0. in Fourier transform because we considered the period is infinity. Fundamental frequency f0 is equal to 0 Hertz. So we must look for a different approach altogether. After all, the DC term can't fit any periodic functions. When I say f is equal to 0, that means what is it? It is a DC term. So let us see how we develop this. So basically the key idea, as I mentioned, is that we think of the period of this aperiodic phenomenon is infinite. So what we will do is we will start with the Fourier series of a periodic function. Let us take a function which is periodic, minus t0 by 2 plus t0 by 2, and then see what happens. Let me take the periodic signal like this. When the period becomes longer and longer or larger and larger till it goes to infinity. Initially it is t0, then slowly increase and allow this t0 to go to infinity. Then let us see how the process changes. So in the limiting process, we will find out how the various frequency components and what their amplitude will be, and so on and so forth. So let me start with a function. This function, let me call this is x of t, and this function is periodic. If you look at here, so let me start with periodic with the period t0. Okay, just to give you a concrete example, I am considering this function. Okay, I will take a specific waveform which is this one, but all our discussion will be completely in general terms. Let us try to understand with this waveform, and then we will develop a separate waveform. Now let us assume the width of the pulse is d. That means what? This point is d by 2 and this point is minus d by 2. Okay, so this is a periodic, what? I gave the name for this, periodic pulse train. Let us say the amplitude is A, and the width is d, and this is minus t0 by 2 plus t0 by 2, this is minus t0 by 2 plus t0 by 2, and this is my waveform x of t, and periodicity being t0. We know the spectrum of this signal, okay, that we already calculated in one of the previous lecture. Okay, so the Cn complex exponential Fourier series is a times d times t0, then sine of n omega naught d by 2 divided by n omega naught d by 2. Okay, so this is something which we have talked about, I think couple of times in one of the past lecture. So let us look at the spectrum of this guy. Now we know that Cn is an even function, and Cn, since Cn is going to be a real number, if you take modulus, then it is going to be a real number, and again here there is no imaginary part, so it is a real quantity. Okay, therefore for real quantity no need to plot the phase. Okay, only magnitude is enough here. Okay, so therefore this function is either positive or negative. The height is equal to ad by t0, and the first 0 occurs, sine of n omega naught d by 2 is equal to 0. That means sine of multiple of pi's. So sine of n omega naught d by 2 is equal to sine of n pi. Sine will get cancelled, then n omega naught d by 2 is equal to pi, n will go. Therefore what is your omega naught? Omega naught is equal to 2 pi by t, right? So that is a point where the spectrum crosses 0. So if you plot it, then it looks like this. It keep on reducing, then this point is omega naught, and this point is 2 omega naught, 3 omega naught, and so on and so forth, and this height is going to be ad by 2. So the nature of the spectrum for a periodic pulse train is not continuous spectrum. It is like this. As I said, It is a trace of the spectrum, but you have a discrete spectrum like this, line spectrum. Okay, so like this, like that. Okay, so what is x of t in this case? X of t is equal to sigma n is equal to minus infinity to plus infinity Cn times e to the jn omega naught t, and Cn is given. Cn is ad by t naught sine of n omega naught divided by n omega naught d by 2. Now how do you find out Cn? Cn is equal to integral of minus t naught by 2 to plus t naught by 2 x of t times e to the minus jn omega naught t dt. Just to recall whatever I did in the previous lectures, the same thing I am repeating now. So this is Cn formula and this is the Xn formula. Okay, these are the two general expressions. Okay, and the waveform is like a square waveform. Now let us see what happens when we have a periodic pulse train, but the period becomes very, very large. So now I will take T naught, this T naught, let me allow this T naught to go to infinity. So let me say this is L. Okay, it indicates a large period. This L indicates a large period, not necessarily infinity, but a very large period. Okay, so it indicates that large period. We have the same waveform, but the next pulse occurs very far away. From this side also it occurs very far away. So now the period is very big. Initially this was my T naught, and this is T naught of L, large period. So I have the same pulse of amplitude A and width also minus d by t2 plus d by 2. Everything is same, but only the period is very, very large. That means the next pulse occurs after very long period. So this guy occurs very long period, after very long period. So consequently the angular frequency corresponding to this guy, let us say delta omega naught. Okay, when the period is long, then what about the frequency? Frequency will be very, very small, right? Because they are inversely proportional, 1 over T naught. If this guy is very large and this will be very small angular frequency. Therefore 2 pi times delta omega is equal to T naught of L times delta omega is equal to 2 pi. Just to recall, your omega naught is equal to 2 pi f naught. So therefore 2 pi is equal to omega naught divided by f naught. Okay, this f naught I can put T naught, 1 by f naught is T naught, right? Therefore omega naught times T naught is equal to 2 pi a. That's what we have written. So instead of T naught I have this T naught of L, instead of omega naught I have small delta omega. Okay, so therefore T naught of large period is equal to 2 pi by delta omega. Now what would be the consequences as far as the spectrum is concerned? Because your Cn is equal to ad by T naught, then sine of n omega naught d by 2 whole divided by n omega naught d by 2. Now look at this coefficient Cn. Okay, this is the formula for Cn. Now what happens if T naught becomes larger and larger? See, this is my T naught. It becomes larger and larger. This is not changing. The sine term is not changing. Sine n omega naught d by 2, because the d by 2 is not changed. and A also not changed. Only thing is T naught is changed. If the denominator becomes larger and larger, then your Cn becomes smaller and smaller, because AD by large number. Okay, so because of that your Cn becomes reduces. Okay, this AD by T becomes smaller and smaller. Okay, so in that case your spectrum will comes down. Originally your spectrum will be like this. Let me draw only very limited period. Your spectrum was like this line spectrum for T naught. Now if you allow T naught to becomes larger, the same spectrum, but now it will be like this. Like this. Okay, so because this is again A naught AD by T naught, right? T naught of L. So this height reduces and this height is AD by T naught. So if you allow T naught of L to go to very large value, then this height of the spectrum reduces. Still if you increase, okay, then what happens in the same spectrum, same zero crossing point, then it becomes like this, very very small. Height becomes reduces, same height AD by T and L. You are allowing T suffix L to increase. When T naught becomes infinity, AD over T naught, if T naught goes to infinity, then the amplitude becomes 0. Therefore you will get a 0 line. So there is no spectrum. Okay, precise. Okay, previously the spectrum between the two lines is omega naught, right? One more point, important point is not only the height reduces, what about the frequency? Originally the frequency was omega naught, 2 omega naught. If I enlarge, this is omega naught, 2 omega naught, 3 omega naught and so on. Now here what happens? This is frequency will be reduces. It is not omega naught, 2 omega naught, it is del omega naught. Okay, so you will get a very closer spectrums like this. Okay, so here the separation between the two lines is omega naught. Okay, but here the fundamental frequencies here in the second case is, it is not omega naught, it is del omega naught, which is smaller. This del omega naught is smaller than omega naught because T naught of L goes to large value. So when you allow the period to high value, then your amplitude is decreasing and also you have so many components, more number of frequency components packed in this region. And here it is also more number of frequency components packed in between these guys. So like this, there are many components because delta omega becomes smaller and smaller. So in this range you have so many frequency components. The whole amplitude comes down, but the whole amplitude comes down. At one point of time it becomes a 0 line when T naught goes to infinity. So now what we really want to know is what happens when T goes to 0. When T goes to 0, this is what happening, infinity, because we want to treat a periodic function as a function of infinite period. When I say a periodic, in that time the period T naught is going to be infinity of the periodic signal. So if T naught becomes infinitely large, then obviously the whole thing squashes down like this. Okay, squashes down to the horizontal line like this, because the amplitude becomes 0. What is amplitude? AD by T naught. When T naught goes to infinity, then it becomes 0. So that will not give us any useful information, right? If the spectrum is 0, then what you understand from this, or what will you get from that? Nothing. Therefore, this kind of argument will not take us to anywhere. So we must see some other way of handling this information. So we need to find out some other method. So what we should like to see is, you have some kind of new quantity which we should plot. So we don't want to plot Cn. Let us try some new quantity. By the way, this is Cn, right? So don't try to plot Cn. Okay, let us do some kind of modification and let us see, can we get any useful information and which will be meaningful, and which will give us an idea of the relative sizes of the various harmonic components. Okay, after all, the whole problem comes here because Cn is like 1 over T naught integral of x of t times e to the minus j n omega naught t times dt, right? So the T naught is in the denominator. If the T naught is in the denominator, then if you allow T naught to go to infinity, then Cn goes to 0. That is a problem for us till now we faced. Okay, what is Cn? Cn is the Fourier series coefficients. It represents the amplitude of e to the j n omega naught t, right? So x of t is equal to summation of n is equal to minus infinity to plus infinity Cn e to the j n omega naught t. What is Cn? It is a coefficient of this component. And again, as I said, this component always occurs in pair, e to the minus j n omega naught t plus e to the j n omega naught t. When T naught goes to infinity, then Cn goes to 0 and these two components also goes to 0. So we don't get any useful information. Now what we do is, now instead of that, if I plot, you bring this guy to the numerator, okay, from the denominator, from the right hand side. Therefore Cn times T naught is equal to x of t times e to the minus j n omega naught t, like this. So now I bring this T naught to the numerator, to the left hand side, so it becomes numerator. When t goes to infinity, then Cn also will be increased up. So that will let us try to see whether it will give the a meaningful result. Okay, now let us plot Cn times T naught of L. So the magnitude is Cn times T naught, where L indicates large value, and here you increase the value like n omega naught, like that. Okay. Now not omega naught, delta omega naught. Therefore Cn times T naught of large value is equal to Cn times, what is T naught of L? T naught of L we said 1 over delta f. Delta f naught, very small frequency, and this we already derived this. What is delta f naught? This is delta times what is f naught? F naught is omega naught by 2 pi, where delta indicates very small. That's what we mean by delta. Okay, now let us try to plot this quantity. So if we plot this quantity, we are going to multiply the Cn by T naught of L. That means, as far as this waveform is concerned, you are going to plot AD by T naught. This T naught is coming to the numerator, so you are going to plot AD times sine of n omega naught d by 2 whole divided by, let me write down here. See, what is your Cn? Cn is equal to AD over T naught sine of, for square pulse. Okay, I am taking the example of this pulse like this. For this kind of pulse, what is Cn? Cn is equal to AD over T naught of sine of n omega naught d over 2 whole divided by n omega naught d by 2. You bring this t to the numerator on the left hand side. So Cn times t naught, you allow t naught to go to infinity. So this is AD times sine of n omega naught d by 2 whole divided by n omega naught d by 2. Now look at the beauty. Even if you increase the t naught, the amplitude is not decreasing, amplitude is, the maximum amplitude is AD. Okay, so therefore we are plotting in terms of Cn of t naught of L. Okay, so the maximum amplitude is what? A times d. Okay, and again it goes like this. So therefore the amplitude is not diminishing now, because of this guy t naught of L is coming to the left hand side. Okay, so now let me draw the two plots. Now when you plot Cn is equal to originally AD over t naught sine of n omega naught d by 2 divided by n omega naught d by 2. If you plot the spectrum, the spectrum will be like this. So you have the components like this. Now if we plot Cn times t naught of large L, then also it is again AD, that's all, sine of, now it is not n omega naught, it is n times delta omega naught, because the L is very large, times d divided by 2 whole divided by n times delta omega naught, small delta, small omega naught, okay, and d by 2. The same amplitude, same height, whatever the height you have here, same height, but you have it packed with so many frequency components, very closer and closer like this, because the distance between the two frequency components is not omega naught, it is delta omega naught. Here these two distance is omega naught, and here these two distance is delta omega naught. Therefore in this interval it is packed with many more line spectrum. So the lines will become closer and closer when you allow t naught to go to infinity. That's what we mean by. But the amplitude remains constant, AD, here also AD and here also AD. We are not disturbing. So the spacing between two particular lines becomes delta omega naught here. And this frequency axis corresponds to what? 2 pi by d, because that is not changing, d is the same. So this point is 2 pi by d. Okay, so we don't want to deal with the Cn, but Cn times, this is Cn times t naught. Then we can think of meaningful way of representation of the various harmonic components. If you think in terms of Cn, then you don't get any meaningful representation, because when t naught goes to infinity, then you will get a zero spectrum, squashes down to 0 to the x-axis. But if you think of in terms of Cn times t naught, then you will get a meaningful representation. Okay, now where Cn times t naught of large t naught is equal to Cn divided by delta times f naught, very very small f naught. And what is the unit of this? This is coefficient per unit frequency. It is not coefficient, it is not Fourier series coefficient, it is Fourier series coefficient per unit frequency, because in the denominator we have frequency. Therefore this is called a coefficient density. It is called a coefficient density. Okay, this is called a Fourier coefficient density. Once you have the coefficient density, then your x of t can be written further as follows. You recall your x of t is equal to sigma n is equal to minus infinity to plus infinity Cn times e to the minus jn, is it minus or plus? Plus omega naught t. Okay, now what you do? You write down the same expression, n is equal to minus infinity to plus infinity Cn. You divide by, let's say, delta omega naught by 2 pi and multiply by delta omega naught by 2 pi times e to the jn omega naught t. Okay, so in this you bring this 2 pi outside, 1 over 2 pi sigma n is equal to minus infinity to plus infinity Cn divided by delta omega naught divided by 2 pi and e to the jn omega naught t times delta omega naught t. I can rewrite like this. Since I have divided by this delta omega naught by 2 pi, I have to multiply by delta omega naught by 2 pi. So that would be the form of Fourier series. Now in terms of coefficient density, see, this is called a coefficient density, Fourier series coefficient density. I am doing all these manipulations to bring it to in the form of coefficient density. Now let us see what happens when you have an aperiodic function, right? In the aperiodic function we still take the same coefficient like this, but now the period t naught to go to infinity. So in the aperiodic function we still take the same function, that is same amplitude a, and this is minus d by 2 and this is plus d by 2. Okay, but there is no other pulse involved from minus infinity to plus infinity, no other pulse, therefore the period is infinity. So what is the consequence of this? When I say the period is infinity, I mean not equal to infinity, when t naught goes to infinity, what is the consequence of this? See, t naught goes to infinity, therefore your delta omega naught goes to 0. That means what? It is not equal to 0. See, when I write delta equal to 0, that meaning is different. When I say delta omega naught goes to 0 means the physical meaning of this mathematical way of writing is like delta omega naught becomes smaller and smaller. That is the physical meaning of this, smaller and smaller. See, there is a huge difference between delta goes to 0 and delta omega naught is equal to 0. Similarly, when I write t naught is equal to 0 and t naught goes to infinity, when I write t naught goes to infinity, that means what? It is becoming larger and larger. Larger and larger. Initially the spectrum is like 0 omega naught, then 2 omega naught, like this, right? Now then what happened? You packed so many frequency components between this, like so many components. Now still you again when t naught becomes this t naught is large, then t naught is some finite value. In this case, if you allow t naught to go to infinity, then within this omega naught and in this interval you have continuous spectrum. It is very, 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 very close. If you expand, then you will see all are very closely placed. That means what? Delta omega naught becomes 0. That means what? It is continuous now. Smaller and smaller, smaller and smaller means what I am trying to say is it becomes continuous range now. See, initially it was discrete and here also discrete but highly packed. But here you put so many lines, hundreds of thousands of millions of lines. Now it becomes continuous like this. Therefore, delta omega now becomes d omega in the above summation. Okay, so in this summation, this guy is going to be d omega naught when t naught goes to infinity. Let me rewrite here. your Cn is equal to 1 over 2 pi summation of n is equal to minus infinity to plus infinity Cn divided by delta omega naught by 2 pi e to the plus jn omega naught t, then delta omega naught. Okay. So this delta omega naught becomes smaller and smaller. The line gets crowding almost next to each other. That's why I put drawn like this at every point on the curve. So therefore at every point on the x-axis I have the lines everywhere. I am not even one point on the x-axis. Therefore we can say that this delta omega naught is the frequency at which a line exists in the spectrum. Now the line theoretically exists at every point on the x-axis. Okay, this line exists every point on the x-axis. So that's what we mean by. So the consequence is T naught becomes larger and larger. So delta omega naught becomes smaller and smaller. That means it is going to be continuous. Therefore n times delta omega naught, it is going to be continuous variable. Continuous variable. That continuous variable we denote by omega naught. So that's how the limiting process occurs. As the fundamental frequency becomes smaller and smaller, the harmonics exist at every point along the omega axis, along the x-axis. So in the limit you will have a frequency component at every point along the omega axis. So the spectrum now would be just like this. It is not like like discrete spectrum, not like this, not like this. Now it is going to be a continuous spectrum like this, like this. It is a continuous. Okay, when T naught goes to infinity, then it is a continuous spectrum. But here it is discrete. Discrete for t is equal to find some finite value. That's what we mean by. Okay, you have at every point, see at every point you have a spectrum, you have some value. You take any single point, it has some values. So that is the meaning for this amplitude. So this is the continuous spectrum. And what is the DC value? Here the center point omega is equal to 0. Therefore the DC value is AD. And the x-axis in terms of omega naught. Previously it was n times omega naught here. Now this becomes in terms of continuous variable omega. So there is no fundamental frequency, second harmonic, third harmonic, and so on and so forth. So we have here is an argument where you have every frequency presents, but the coefficient density corresponding to each frequency is different. So in this it is Cn, and here this is going to be Cn times T naught of L. So this is the coefficient density. Okay, so that is the difference. Here it is Cn and here it is Cn of T naught of L. Let me write down clearly. C naught times T naught of L. This is the coefficient here. Okay, now let us give the name for this guy. So this is named as x of j omega. Okay, so therefore now the question is, how do you get this x of j omega? Now Cn is given by the following formula. Like we know that Cn is equal to 1 over T naught integral of minus T naught by 2 to plus T naught by 2 x of t e to the minus j n omega naught t times dt. Now you bring this guy to the left hand side. So Cn of T naught is equal to integral of minus T naught by 2 to plus T naught by 2 x of t e to the minus j n omega naught t and dt. Okay, so this formula is applicable to the aperiodic case also. Now what is the period in this? See, this is a formula actually for a periodic. Now we are trying to use a periodic also. So in a periodic, what is the period? T naught becomes infinity, right? Therefore Cn times T naught, the period becomes minus infinity to plus infinity. X of t times e to the minus j in omega naught t and dt. Now look at this n omega naught t. N omega naught t becomes continuous frequency omega. Okay, so n omega naught t becomes omega, continuous frequency. It is a continuous running variable. Therefore, this is we have given the name, that is x of j omega, and this is equal to integral of minus infinity to plus infinity x of t e to the minus j omega t and dt. And this one is called Fourier transform of what? Fourier transform of x of t. That's it. Okay, and this x of j omega is called the coefficient density in the periodic case. Coefficient density in the periodic case, it is coefficient, Fourier series coefficient, and here it is coefficient density for a periodic signal. Recall from the Fourier series, there we say coefficient simply, but here it is coefficient density, and which is given by integral of x of t e to the minus j omega t dt, and the limit is from minus t to plus t. What is the corresponding formula for Fourier series? Cn is equal to 1 over t naught, because the period is finite, minus t naught by 2 plus t naught by 2 x of t e to the minus j n omega naught t dt. That's it. So instead of Cn, we need to deal with the x of j omega. Okay, so in this case here x of t is periodic, and here x of t is a periodic. When I say a periodic, then t naught goes to infinity. Okay, now recall from your Fourier series, what is your x of t? Just now we have derived this. Let me rewrite this formula. Okay, where is it? Yeah, this one. Now this one, you rewrite this. Okay, now we have to take the limit this as delta omega naught t to go to 0. Okay, so let me write down in the denominator somewhere else. One second. I'm sorry, this is not Cn, right? It is x of t. I'm sorry, I have written wrongly this one. Let me write down one more time. X of t is equal to 1 over 2 pi sigma n is equal to minus infinity to plus infinity Cn over delta omega naught over 2 pi, then e to the minus jn delta omega naught t delta omega naught t, then delta omega naught. Okay, now you take the limit of f of t, that is t naught. What is the limit? T naught goes to infinity. That means what? Del of omega naught goes to 0. Therefore x of t is equal to limit del of omega naught to go to 0 1 over 2 pi integral of n is equal to minus infinity to plus infinity. And what is this? Just now we have derived this. This is the Fourier coefficient x of j omega. X of j omega. Okay, so x of j omega times, then this n times omega naught t, we said omega, so e to the minus j omega. I'm sorry, there is no minus here, I wrote wrongly. Originally there is no minus, it is a synthesis formula. J n omega naught t and j omega t times delta omega. Okay, now this delta omega goes to a continuous running variable. So let me put d omega, that is. Okay, so here what we did is like n times delta omega naught becomes continuous variable omega. When n goes to minus infinity, then omega also goes to minus infinity as per the limit is concerned, as far as the limit is concerned. And when n goes to plus infinity and the omega goes to plus infinity, right? Therefore, this x of t is equal to limit delta omega goes to 0, 1 over 2 pi, then summation over n is equal to minus omega to plus omega. Wait a minute, I am sorry, I am writing some blunder here. Omega naught is equal to minus infinity to plus infinity, then x of j omega e to the j omega delta omega. Now in Fourier series, f of t can be thought of as a summation of the several exponential functions like this. Not like this. One second. In Fourier series, what we said, Cn is equal to summation of Cn times e to the j n omega naught t. Several components, minus infinity to plus infinity. But here, in this one, what we really have is x of t is consisting of a similar exponential function e to the j omega t, where omega take any value from minus infinity to plus infinity. Okay, see here, this omega takes any value, from minus infinity to plus infinity, continuously takes. Therefore, what you do is you replace the summation by integration. So minus infinity, omega is equal to minus infinity to plus infinity, x of j omega e to the j omega t, and this del omega becomes d omega. So 1 over 2 pi, this is your x of t. Okay, so you are integrating that x of j omega times e to the j omega t over the complete omega axis from minus infinity to plus infinity. Okay, and this is your x of t, and this one is called Fourier integral. Fourier integral. So instead of series, we have an integral. So in the previous case, we had a summation like this, Cn times e to the j n omega naught t, then n is equal to minus infinity to plus infinity. So here we had summation, and here we have integration. So that is why this is called a Fourier integral. So similarly, instead of calculating the Fourier coefficients like this, you can calculate the coefficient density x of j omega. Therefore, we have two formulas. One is Fourier integral, this one, and the Fourier transform is x of j omega. Instead of Fourier series coefficient Cn, we are calculating x of j omega. So this is integral of minus infinity to plus infinity x of t e to the minus j omega t times dt. And this 2 pi arises because we are calculating about Fourier coefficient density in terms of what? In terms of frequency f rather than omega naught. So that is how it is conveniently defined. The denominator frequency is hertz, okay, rather than radius per second. So, and secondly, we can sometimes people used to call this as x of omega, but we will stick to this notation x of j omega because it is function of the exponent e to the j omega. That's why. Okay, because later on we would like to relate the Laplace transform where f of j omega can be thought of as a special case of f of s. Okay, sorry, x of j omega can be thought of a special case of x of s, where x of s is the Laplace transform of x of t. That's why. Therefore, it would be convenient to put x of j omega rather than x of omega. Okay, we will stick on this notation. Okay, so that's it about the introduction to Fourier series, Fourier transform. Okay, so we started with the Fourier series. So Fourier series is applicable to only periodic. Now we looked at, is there any possibility to analyze aperiodic? Surprisingly, the answer is yes, but aperiodic can be treated as periodic with period t0 to go to infinity. So in that case, we calculated the Fourier series coefficient density x of j omega rather than the coefficient Cn itself. So in the periodic case, the spectrum is discrete like this, but here the spectrum is continuous. That's it. Okay, so that's all about the introduction to Fourier series. Okay, so let me stop at this point. Thank you very much.